Welcome to this video on discrete probability distributions part 1. After watching this video, you should be able to define the term random variable, state the difference between discrete and continuous random variables, and determine whether a given random variable is discrete or continuous, state the requirements for a discrete probability distribution, and determine if a given table satisfies these requirements, find a missing probability in a discrete probability distribution, graph a probability distribution, and lastly, describe the shape of a probability distribution. What is a random variable? A random variable measures the outcome of a probability experiment. Random variables are usually associated with frequency distributions. If you recall from a previous section, a frequency distribution will look like this. And in the left-hand column, we have an outcome, and on the right-hand side, we have a frequency or relative frequency. The value of the random variable is determined by chance. The value of a random variable can vary, therefore, with each repetition of an experiment. An example would be flipping a coin. Every time you flip the coin, you're not really sure whether it's going to land on heads or tails. Random variables are represented with capital letters such as x. Random variables can be either discrete or continuous. Review of discrete versus continuous random variables. A discrete random variable represents a count. When plotted on the number line, a discrete random variable can only assume certain values. For example, if you were counting the number of students in a class, there could be 17 students or 18 students, but a count of 17.5 students is not meaningful. A continuous random variable represents a measure and can assume infinitely many values. The precision, or the number of digits after the decimal point, is limited only by the instrumentation used to measure the value. For example, the distance between 2 points could be 1.4 miles or 1.41 miles or 1.416 miles, etc. There is no limit to the amount of precision that could be provided, only a limit to the amount of precision that is useful in the particular application. For a more thorough review of discrete versus continuous random variables, please watch my video entitled Data Types. Discrete random variable example. Suppose a person flips a coin 4 times. Let's define x, the discrete random variable, as the number of heads observed during those 4 flips. What are the possible values of the random variable x? Well, first of all, what is the fewest number of heads that could occur in 4 flips of the coin? Pause this video, write down your answer, and then unpause it to check your answer. If you said 0 heads, you are correct. All 4 flips could land on tails. What is the largest number of heads that could occur in 4 flips of the coin? Again, pause the video and write down your answer. If you said 4, that is correct. All 4 coin flips could result in heads. So, what are the possible values of x, the random variable? It could be 0, 1, 2, 3, or 4. Because it is a discrete random variable, values in between, for example, 0 and 1 or 1 and 2, are not meaningful. They have to be whole numbers. These are often displayed in a table called a discrete probability distribution, such as the one shown here. So on the left-hand column, we have the values of our random variable x, and on the right-hand side, we have the probability of each event. Identifying discrete random variables 1. The Highway Department is going to inspect a randomly selected 1-mile portion of Interstate 95 looking for potholes. What is the random variable x in this example? Pause this video, write down your answer, and then unpause it. The random variable is the number of potholes found in the 1-mile portion of I-95. What are the possible values that the random variable could assume? Well, the smallest number of potholes that they could potentially find is 0. So we write 0, 1, 2, 3, 4. Notice that there is no upper limit on the number of potholes that a person could find in a 1-mile stretch of road. So we use these 3 dots, which are called an ellipsis, to indicate this idea that there is not an upper limit. Identifying discrete random variables 2. A hospital administrator is interested in the number of vacant beds in their hospital on a given day. What is the random variable x in this example? The random variable is the number of vacant beds in their hospital on a given day. What possible values could the random variable assume? Well, the fewest number of vacant beds could be 0. So we have x equals 0, 1, 2, 3, 4. The upper limit of this random variable would be the number of beds in the hospital. Since we do not know this value, we use an ellipsis to indicate that the upper value of x is unknown. Identifying discrete random variables 3. Suppose you are practicing free throws on a basketball court. You decide to count how many baskets you make out of 10 shots. What is the random variable x in this example? The random variable is the number of shots you make. What possible values could the random variable assume? Well, x could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. Notice that the upper limit of this random variable is the total number of attempts, which in this case is 10. However, instead of listing all of those numbers, we use an ellipsis to abbreviate the list of possible values, even though in this case there is an upper limit. What is a discrete probability distribution? A discrete probability distribution is similar to a frequency distribution. In the left column, all possible values of the discrete random variable are listed, and in the right column, the probability or relative frequency of each of these values is listed. Here we have a frequency distribution, which we learned about previously in this course, and here we have a discrete probability distribution. So again, this is our frequency distribution, this is our discrete probability distribution. Let's compare these two tables and see what similarities they have and what differences they are. Pause this video, write down your answers, and then unpause it to see if you're correct. So one difference you might notice is that a frequency distribution generally has classes or bins on the left-hand side, whereas a discrete probability distribution has these values of the random variable, which should be discrete numbers, usually whole numbers. So that's one difference. Can you see a similarity? One similarity is that the right-hand side is usually a frequency or relative frequency. Over here, for a discrete probability distribution, it has to be a probability or relative frequency. In other words, a number between 0 and 1. If you're working with a frequency distribution, it could be a count or it could be a relative frequency. Requirements of discrete probability distributions. Just like any other probability distribution, a discrete probability distribution has these two requirements. First of all, the sum of the probabilities is 1 or 100%. Secondly, all the probabilities must be between 0 and 1 or 0 and 100% inclusive. Notice that the second requirement implies that the probabilities cannot be negative. They must be either 0 or a positive number. Which of the following is a valid discrete probability distribution? Remember, the requirements are that the sum of the probabilities is 1 and that all the probabilities are between 0 and 1 inclusive. Let's look at this first probability distribution. Pause this video and write down whether or not you believe this is a valid discrete probability distribution. Then unpause the video to check your answer. Notice that if you add these probabilities together, you end up with 1.01. Therefore, since the sum of the probabilities is more than 1, the first requirement is not met. So this is not a valid discrete probability distribution. Let's look at another example. Again, pause this video and write down your answer. Is this a valid discrete probability distribution? The answer is no. First of all, one of these probabilities is more than 1, and one of them is less than 0. It's negative. So even though they add up to 1, because these two values do not meet the second requirement, this is not a valid probability distribution. How about this distribution? Again, pause this video, write down your answer, and then unpause it. So this is a valid probability distribution. All the probabilities are between 0 and 1 inclusive, and when you add them together, the probabilities sum to 1. Complete the following discrete probability distribution. If we look at this table, we can see that all of the probabilities are given to us except for this one value right here. Let's assume the table to the left represents a valid discrete probability distribution, which means that the probability is summed to 1, and all of the values will be between 0 and 1 inclusive. Find the value of the missing probability. Again, the probabilities have to sum to 1, so we begin by adding the given probabilities. Doing that, we find that the sum of the probabilities that we are shown is 0.85. We know that 0.85 plus the missing probability has to give us 1. So we can just use a little bit of basic algebra to solve for our unknown quantity. Doing that, we find out that the missing probability is 0.15. Graphing a discrete probability distribution. Suppose the discrete probability distribution shown here represents the probability of the number of cookies X a person will eat out of a bag of 5 cookies. Create a graph of this discrete probability distribution. The first thing we need is a title. Well, what is this problem about? It's about the number of cookies that a person eats, so we'll call the graph eating cookies. Then we need an x-axis. Which of these two values goes on the x-axis? If you said the number of cookies eaten, x, you are correct. We always put the random variable on the x or horizontal axis. Next, we need to put tick marks on our horizontal axis, and notice that we start at 0, which is our smallest value of our random variable, and we go all the way to 5, which is the largest possible value of our random variable. What do we need next? Well, now we need a vertical axis. Notice that our vertical axis should start at 0 and go all the way to 1 or 100%. This is the probability, or the values from this right-hand column. Now that we've set up our graph, we can start plotting these values. So if a person is going to eat 0 cookies, the probability of that event is 0.1 or 10%. So we draw a vertical line starting at the bottom and going up to 0.1. If a person eats 1 cookie, the probability of that event is 0.2 or 20%. So again, we draw a vertical line, and this time we make sure that line goes up to 0.2. The probability of a person eating exactly 2 cookies is 0.25, 3 cookies is 0.05, 4 cookies is 0.15, and 5 cookies is 0.25. So this is what a discrete probability distribution graph will look like. Describing the shapes of discrete probability distributions. Previously in this course, you learned how to use the terms unimodal, bimodal, multimodal, and uniform to describe the shapes of graphs. You also learned to determine whether graphs were symmetric, skewed left, or skewed right. We will use the same terminology to describe the shape of discrete probability distributions. To review this terminology, you may wish to watch or rewatch the video entitled Describing the Shapes of Histograms. Having watched this video, you should now be able to define the term random variable, state the difference between discrete and continuous random variables, and determine whether a given random variable is discrete or continuous, state the requirements for a discrete probability distribution, and determine if a given table satisfies these requirements, find a missing probability in a discrete probability distribution, graph a probability distribution, and lastly, describe the shape of a probability distribution.